My name is Christian von Koenigsegg. I'm 40 years old, and for half of my life I've been on the quest to be a leader in the hypercar industry, utilizing Swedish design combined with visionary technical solutions. So this is the one-to-one, getting ready to be shipped out to the Geneva Motor Show in about 4 or 5 hours. We've been pretty much working flat out day and night for the last couple of weeks to get to this point. So it's a great relief, even though we always kind of make it. It's always good to see that it's happening this time as well. So the one-to-one is our most extreme car ever created. It's 1 horsepower per kilo of weight, and that's curb weight. That's with fuel or liquids, ready to run car on the street. That's never been done before. Interestingly enough, 1360 horsepower, which is the power level of the engine, is also pretty much exactly 1 megawatt of power. Thereby we think this is actually the first Megacar ever produced, which is quite exciting. So basically it's establishing a new category. Not only the most power per kilo or weight, but also the most powerful production car ever built, and it's 1 megawatt of power. So that combination is just going to be fantastic on a track. So it's very extreme when it comes to all the aerodynamic features. For example, here is a good example. We have removed some of our luggage space and put in these air ducts going into the front bonnet, and we've covered up some other air outlets into the front subframe. We have these huge winglets and splitters, which also have active elements underneath the front splitter that move around depending on aerodynamic downforce needs. We can't see it right now, but the shock absorbers are also active in ride height, individual left and right side, front and rear, but also rebound and compression settings are individual on each damper on each 4 corner. And this can act dynamically around a racetrack to reset itself while you're driving. And it's all hooked up to a cloud over 3G. So our customers will be able to download data for different tracks and really have maximum performance in every given condition. So even though we added a lot of extreme functionalities, aerodynamic elements, made the car stiffer and stronger, stronger engine internals and so on, it's still lighter. Basically, we added about 30 kilos of weight in componentry and functionality, but in total the car is around 80 kilos lighter. And even though this is the first development car and some of the components in the interior are prototype and a little bit heavier than the production versions, we're almost hitting the 1360 target already with this car in this show condition. And the production car following this car is estimated to be 30 kilos lighter than this. So that will actually probably be lighter than 1360 kilos as it looks like. So that's really, really fantastic. Here you can also see the huge active rear wing, which is now set in full brake mode, flipped up. So in that position, it's actually giving the largest amount of downforce that it can with the largest amount of drag. So it's not only an aero brake, it's also giving maximum amount of downforce to the rear wheel simultaneously. And that was possible due to the unique shape of the wing that follows the contour of the car, but also is a double wing with 2 aerodynamic elements interacting, so the stall angle is higher than it otherwise would be. We can also go around here and see the interior a little bit that's coming together. It's a striking black Alcantara lightweight interior with orange elements matching the outside of the car, with new clear carbon elements on the interior that we used to cover up before, but now we're leaving them bare naked to save weight and give a more racy look. So this car is really, when you take it to the track and you put it in the lowest setting, it's really a full-on GT1 car specification, apart from the fact that it has more than double the amount of horsepower. But when you go on the normal road, the car raises itself up, the suspension becomes softer, it even has power windows, air conditioning, amplifiers, 6 speakers, anything that you would find in our normal cars are still there, even though we have this huge weight saving. When we come to the back of the car, we can see this exhaust end piece, which looks similar to our normal ones, but it says 1-to-1 titanium, and we have new air outlets underneath here for greater gearbox cooling, and it's one of the world's largest 3D printed titanium pieces ever made. It's a Swedish company making huge 3D printing machines that's made it for us. It's also a very local product. We're also printing our variable turbine housings for the turbos that we developed for the car to have a huge power range. They are so complex in shape that they're difficult to cast, and in our low volume it makes full sense to actually 3D print them even for production. So that's also very unique. And it makes it possible for us to have over 1,000 Newton meters of torque from under 3,000 RPM to up to 7,800 RPM. So the power curve and the range of available power over the registry of the RPM is just previously unmatched by any other car. So we're very happy about that. Here we can actually see the active suspension system. Here we have a hydraulic lifting system actuating on the springs on the rear, and then we have electric controls over compression and rebound damping here. We're actually going to put carbon fiber springs on the production cars as well to even further save weight, and we will start testing that when we are home from Geneva, from the Geneva Motor Show. So this car will actually, as soon as the Geneva Motor Show is over, we will start to use it for test driving and setting the car up. So far we've just driven around the shop with it. All driving with it before that has been virtual on the computers. And it will also go to the Beijing Auto Show in April. And after that, it will really start hitting all the European racetracks in a serious way to get it, well, fully shaken down and tested before we start production of the customer cars. So the 1-to-1 engine is based on our Agera R engine. So we always kind of work in steps. It's an iterative process where we keep on pushing the boundaries and fine-tuning and finding solutions. So in order to get the power at an even higher level than what we have in the Agera R, we have reported the cylinder heads. We have changed valves, springs, retainers, camshafts, camshaft drive, injectors, fuel pumps, fuel system, turbos, partially the exhaust system. Those are basically the physical changes to the engine. And then there's a lot of software tuning to get it run properly. Given all these changes, we've been able to raise the RPM level, and thereby we can get, and given that we have different camshafts, we have more power higher up in the RPM range. The good thing about that is we're not putting more strain on or more torque into the parts or the block, because we're getting the power at a higher RPM level. So that means we don't have to reinforce the rest of the engine. We just had to make all the parts light enough in the valve train and drive train to take the higher RPM. So yeah, those are the physical changes. The engines are completely built here from scratch and are unique to us. So in the one-to-one engine, the first prototype one-to-one engine we've been working on for 3-4 months, speccing up, simulating, assembling, checking flowing ports, checking that we have the right compression ratio for the need, and we just started running the engine a few days ago on the dyno. And it will be on the dyno for a few days, and then it will go into the test car, and then we will start running another one-to-one engine on the dyno, further refining it to get that program also into the first test car. We try to keep it lean, minimalistic, only put in exactly what we need to get the job done and to get the performance we need, or the drivability or the comfort or whatever. I think all these hybrids coming out now is an answer to trends and ideas connected maybe also to some of the manufacturers' more normal cars to market them. And it's really tough with today's hybrid technology to compete with a non-hybrid car that is optimized, because they become heavy and complex and dual systems gets involved, and that has to work together. You can get a good result, that's proven, but I don't think you can get as good result as doing a car without those systems today. Maybe at a point in time in the future these systems will be optimized, but that's not what we see is happening right now. Also, I think when you get better batteries and better electric motors that are in these hybrid cars, you will be better off making an electric car than a hybrid car. And while the, let's say, normal combustion engine is developing also still rapidly, it will be better off in many ways without a complex hybrid system by itself. So it's kind of avoiding trying to mix oil and vinegar, basically, from my point of view. And I think we're already proving, and we will continue to prove, that it is in many ways better not to do it. Rear wing ever made, as far as we are aware. The reason why it's top mounted is because the most important part of the wing is the underside to create downforce. It's like an upside down airplane wing where the top side is the most important. So traditional wings are mounted from underneath, which is the simplest solution, but then you actually take away an important area for downforce creation, more important than the top side. So if you look at modern Le Mans cars, they usually have pylons sitting in front of the wing, going up and then down, holding the wing from the top. But the difference between that and our solution is that they have the wing mount just in front of the trailing edge, causing still quite a lot of turbulence behind the mount, even though it's top mounted. So we kind of came up with this idea to mount it in front of the wing and tapering it up so there is no turbulence creating a mount just in front of the wing. So not only is it top mounted, not only is it active, it's also more front mounted than top mounted. Another side effect of these strakes, as we call them, is that they actually stabilize the car at high speed as well. They become like rudders, and they don't increase the frontal area compared to normal traditional mounts. So it's basically only positive side effects of having this design compared to traditional solutions. So high speed stability, less turbulence in front of the wing, no mount under the wing, top mounting and active mounting. The total weight of this system is around 9 to 10 kilos, which is about a third of the weight we've heard of other active rear wings that our competitors use. So it's really, really lightweight. It's all carbon fiber. Even the rod going from the actuator here at the back of the bulkhead is hollow carbon fiber. It's actually, this logo here is a mount with 2 rubber rollers to stabilize this thin and lightweight rod, so it works, has a good longevity and stability. So it's a kind of an interesting system we came up with, I think. So we're going to demonstrate a little bit and test run the wing function. So this is right now a setting for high speed. This setting has been simulated up to around 450 kilometers per hour. It's minimum drag, minimum downforce, just to make it as slippery as possible. And then we can go into full brake mode, which is, let's see, this setting. So this setting is actually giving the maximum amount of drag in combination with not stalling the wing fully, so we get a super high downforce on the rear wheels for braking as well. So it's not only an aero brake, that's part of the functionality, putting it in this position. It's also maximizing the amount of downforce at the same time. And it's the only aero brake wing working in that way. And the reason why we can do it is because it has such a nice configuration with a twin, with a double wing, so they're helping each other, so you can have it at a higher degree without stalling it fully. It's semi-stalled, but it's still giving a ton of downforce and a ton of drag at the same time. I'm very excited by it, and it's kind of, I've seen the car as a whole on computer renderings and on the computer screen and so on, and it looks kind of massive when you see it that way, especially this area. It looks huge, but when you see, I saw the car on the ground for the first time 2 days ago with the wing on it, and for some reason it looks like the smallest car we've ever made, because the car set into proportion to this big wing makes it shrink into a more realistic size that it is. When we've had smaller wings on the cars and we've had smaller attributes and smaller winglets on the front, the car looks actually bigger. So it's kind of a shrinking dynamic effect to the look when I see it in reality. As the chassis is active and the aerodynamics are active, we don't want to differentiate between the two. It can be like set up for perfect handling on a flat road course, like a go-kart setup, very stiff springs, very stiff shock absorbers, high degree of downforce, stiff dampening, or for the Nürburgring where we race it a little bit and soften up the suspension and the spring settings. So I don't really want to differentiate it from being a mechanical grip car and aero grip car. They work together. Traditionally, we started out with fairly low amount of downforce on our car, so we had to work really hard on the mechanical grip. We still maintain that knowledge and technology and have enhanced it, combined it with the latest Michelin Cup 2 tires and super efficient downforce aerodynamics, and lightening the car at the same time, making it more powerful at the same time. So it's kind of raising the bar in all different directions. So it's going to be a blast to drive. Almost all parts of a Koenigsegg is made out of carbon fiber, and we only use the most extreme type of carbon fiber material available, which is called pre-preg. It's the same that's been used in Formula 1 and fighter jets and spaceships and things like that. It's a pre-impregnated fiber with 2-component epoxy. Usually it's a weave format, so it's woven. It can be different types of fibers for different purposes and different type of weave patterns for different purposes. And we apply them layer by layer in different thicknesses depending on what part we make and what need we have. So right now this is very flexible. It's a little bit sticky, almost like a sticker decal. And we apply it into a negative tool. In this case it's a carbon fiber wheel tool. We're the world's first car manufacturer to make carbon fiber wheels, actually, and it's the most important most important area of the car to have really light weight, because it's rotational unsprung mass. So not only is it bumping up and down, it's also rotating. So you have to accelerate it and deaccelerate it when you're on the throttle and on the brakes, and when you're turning, you have centrifugal forces getting into the wheels and disturbing your steering feel and things like that. So one of the most important things on a car to make really light and strong and stiff are the wheels, and that's why we make them out of carbon fiber. as carbon fiber is the strongest, lightest, commercially available material there is. So what we're seeing here is a layup, and we will follow this process through baking and demolding and polishing, so you will see how that happens. So we've been producing carbon fiber wheels now for our cars for 1.5 years. So it means that almost 20 sets of wheels have been made for production cars, but also for prototypes. And it's something we're very proud of, to have this technology in-house, as I'm aware we're the only ones in the world making carbon fiber wheels for production cars. So what we're seeing here is the first stage, and here we're getting to the second stage, where we have the other part of the tool, which is the barrel area. And as you can see, there are several different layups of thicknesses of carbon and different types of weaves and different types of overlapping. And it's very critical to have stiffnesses in this area for handling, because you don't want to have, even though the wheel is safe, you don't want it to flex in this area because it dilutes your camber settings. So we pay a lot of attention to have perfect stiffness, much stiffer than most racing aluminium wheels even. What you don't see here is the very intricate area of the spokes. As the spokes are hollow and the center of the wheel is also hollow, it's a very special process to make that happen, really, and it's one of the proprietary technologies we have, so we can't show it on camera. But now what we're doing is we're packaging this into a vacuum bag to debulk it and compress the material before it's going into the autoclave, where it's baked under pressure and the material is compressed together. So many people might think this is difficult to balance, as it's laid up by hand and you have all these different layers and so on. But what we've noticed is that they are intrinsically more balanced than casted or forged aluminium wheels. What we actually do is we have the only metal part in the wheel is the valve to fill up air into the wheel. And we have noticed that we tend to have to put balance on the other side of the wheel to where we have the valve. And of course a light wheel is more sensitive to the imbalance of the valve. So what we do is actually on the spoke on the opposite side of the valve, we put a little bit of extra ballast carbon fiber there to pre-balance the wheel already in production. So we need very little weighting on the wheel when we put the tire on. Of course the tires themselves have some imbalances that we also try to match to the wheel's natural imbalance, so they balance each other out. So sometimes we take the tire off and on of the wheel to match it as perfectly as possible in order to have as little dead weight on the wheel as possible. Yeah, so we're now preparing the wheel for autoclave curing. So it's going in a vacuum bag, and this is a breather felt to make sure we get a good spread of the pressure over the wheel, the pressure difference, so there are no voids that get stuck. What you can see here is probably the coolest part of our wheel is that this is a cutout of a spoke, and the spokes are actually empty and hollow. Even the center of the wheel is hollow. And you can see it's also smooth on the inside, so we have a very special process to make this happen, which we developed together with the wheel. And just to understand how strong this wheel is, if you do carbon fiber the correct way with the right material, the right layup and the right fiber type, simply explained, you can consider the thickness of the material to be as strong as if it was this thick and made out of steel. So then you can imagine how strong a tube section like this is, and especially in this area when you see how thick that is. So it's an immensely strong and reliable wheel, but still extremely lightweight. So when it comes to safety aspects and let's say potholes and flat spot and curbing a wheel like this, first of all, when it comes to kind of impact from sharp edges like sidewalks and potholes, a wheel like this will survive a much harder impact than a forged aluminium wheel before it loses its air pressure. So from that aspect, it's a safer type of wheel. And you can't really flat spot it. It's either okay or it's damaged and broken, but it takes much more force to break it than an aluminum wheel. So that's also a good thing. When it comes to kind of curbing it and scratching it, of course you will break the nice outer layer weave, but as long as it is not too deep, you can repair it. You might get a visible difference to the wheel, but it will still be fine to drive with. But as these wheels also are very aesthetically, well, the aesthetic factor is also very important. I would say most people who get really heavy curb scratching would probably replace it, even though it's fine to drive with. So here we have a final produced wheel, and the finish of the part coming out of the tool is actually so good that we only polish it. We don't put a layer of clear coat over it. It's no pinholes and perfect tooled surface. And the nice thing when you polish carbon fiber, you get a really distinctive checkered effect look for this kind of flip-flop between black and silver. It's very distinctive. And of course, not having clear coat and instead it's just raw carbon, it's actually more difficult to scratch it as well. It's a harder surface than an acrylic paint would be. What we do is we polish it and wax it with a UV protective kind of wax surface, just to have a little bit of UV protection to it. But this type of carbon fiber and epoxy does not yellow over time, so it stays like this pretty much forever. You see from the back side as well. So it's just carbon here, and it's actually hollow inside. You can, if you put your finger in here, you can feel the hollowness inside the wheel. So as I said before, the only metal part normally is this valve up here, which is not put into place yet. So this is a 19-inch high and 10-inch wide front wheel. In the rear we have 20-inch high and 12.5-inch wide. Before the carbon fiber wheels, we had forged aluminum wheels, which were very, very light. The front wheel was around 10 kilos. This one is just under 6 kilos. It's 5.9 kilos. So it's about a 40% weight saving to the lightest forged aluminum wheel there is, pretty much. So just to show you on camera what that means, I can take it in my finger here, just lift it like that. Not that heavy. I think when people hear that we're using carbon fiber wheels, they kind of start thinking, ooh, it must be difficult when you hit a curb to make it strong enough, or even potholes and or sidewalk edges and stuff like that. But that's kind of easy compared to handle, compared to the fact that we have these massive, huge brakes generating incredible amounts of heat. Stopping the car from 300 kilometers to 0 in 6.6 seconds. It's just a massive generation of heat. So in order to cope with that and make sure the wheel withstands that heat, we have to work with very special pre-preg material, with very special epoxies and after treatment processing to get the wheel to take that heat in a good way. So yeah, that was the biggest challenge, and something we're very proud of to have overcome. So we just revealed our latest one-to-one model at the Geneva Motor Show. And this is also a good opportunity to show you our latest turbo technology, our variable 3D printed turbo technology that also goes into the one-to-one car. So this is an idea we came up with a few years ago to make sure we have as wide power range as possible with reasonably sized engine. So if you have basically a big turbine housing, it means you can get a lot of exhaust gases rushing through it and drive the turbine hard at high RPM without creating too much back pressure and increasing the risk for knocking with hot EGR gases. At the same time, that's not very good to have a quick spool up of the turbo at lower RPM. Then you want a small turbine housing. The problem with a small turbine housing is the opposite. It spools up the turbo quickly at low RPM because it makes it narrow and tight for the exhaust gases around the turbine wheel. So it gets more jets directed to the wheel and thereby spooling it up quicker. But then you get more back pressure at high RPM because then it's restricted. So I had an idea where we made kind of two housings in one. There is an inner house close to the turbine, which we have open first to get the kind of a quick spool up I was just mentioning with a small turbine housing. And then we move a lever and open up a second chamber area, which is a bigger turbo housing, so that when the turbo has already spooled up, we can reduce back pressure and get a freer breathing at high RPM. So there are other variable geometry turbos around which are more complicated than this with many louvers. So this is simplified, can take a lot of heat, and it has some very unique features around the turbine wheel. So the two different chambers in the turbine housing, they twist around each other, and the intermediate wall is bending around in a diagonal fashion around the turbine wheel to optimize the flow of both chambers. So that we have a patent for. And this is actually 3D printed. It's quite complex shapes in here. So it's difficult to cast when the chambers are kind of twisting around each other. So we tried to cast it at first, and I guess with a lot of trial and errors we could have made that work. But with the modern 3D printing methods, you can actually print at a relatively good price for low volume in stainless steel or titanium. So we have, for our production cars, we're actually printing these in stainless steel, and we're printing the moving parts as well at the same time internally in the housing, so we don't need to fit them afterwards. They're already in there when we get the turbine housing. Also, the threads to mount the turbine housing are 3D printed in the process, so there is very little to almost to nothing in retro finish surfacing work. So all in all, it's a very interesting, unique solution that gives our engine a broader range and a unique capability for its size. So I'm going to talk a little bit about 3D printing and laser scanning technology we use here at Koenigsegg. These tools are getting more and more common and more available to anyone, but I guess we have implemented a very straightforward and efficient way of using them. And I would like to start to talk about our new one-to-one seat. This came quite late into the program. We felt we really needed to save weight and get an even more race-inspired seat. And to design a seat from scratch in the computer without being able to sit in it, most likely will not end up in a very comfortable seat or space efficient or optimized. So what we did was we basically started cutting and shutting together this very rough model inside a monocoque chassis of a car. And I sat in it, and some other people sat in it, and we tried all these different types of cushions and things, and we were sawing and laminating and filling with filler and just roughly cutting it together. It's not even 100% symmetrical, but that doesn't really matter as long as it's fairly even and you can get a feel for what it is. Then when we were happy, we took our laser scanner. We threw out these kind of small dots everywhere, so the laser scanner eye here can track exactly where the seat is in the space, and you can move it around with no problem. And then we laser scan this like this from different angles, and then it pops up onto a laptop screen and becomes what we call a cloud file of dots. And then we can throw that in computer and create skins and perfect Class A surfaces and perfect symmetrical shapes. So this project we started just shy of 4 weeks ago, and tomorrow night the first one-to-one development car will leave with 2 almost production-ready version of those seats for the Geneva Motor Show. So from idea, trying to sit in something, to CAD file, to tool, to 2 carbon fiber seats with custom-made foam and leather pieces and everything in 4 weeks. Just to explain how fast it's possible to work when using this kind of empirical backwards and forward methodology between 3D CAD and reality. So many of the parts, of course, we first 3D print off of CAD data to try in the car. This is a new one-to-one brake pedal. This is a new one-to-one throttle pedal. They are machined normally out of aluminium. They're adjustable for different angles and length of legs and so on. And this way we could try them in a car. I wouldn't want to go driving on a racetrack with these, but you can sit in the car, see how they feel, try spring loads, try positions. If needed, modify them by hand until they're exactly how we want them, and then we laser scan them and throw them back into the computer again. So we printed out this piece, tried it in a car, this footrest, 2 different positions for comfort and spirited driving. And then we modified that by hand, laser scanned it, refined it in the computer, printed an aluminum tool with this shape, and we made this carbon piece for the first one-to-one car. Also, this happened in like a 7-8 days period from first idea to finished product. So you can move really, really quickly. Foot for new wing mirror housing, which we could try on the car. We first CFD'd it in the computer to check the aerodynamics, and then tried it on our test Agera to see how it worked in reality just by printed plastic. This is ABS plastic. It's quite a good, strong material to print out of, which is actually long-lasting over time. And we actually, since the last 4 or 5 years, we have been printing air ducts for HVAC units and stuff like that, and some air guides from the front wheel arches, a few bits and pieces, interior pieces in the wing mirror for production cars actually, out of this material. So in low volume, it makes sense to print parts which are fairly arbitrary and not very highly loaded, like guides and things like that. But in the last few years, it also has came up the possibility to print metal parts in titanium, aluminum, steel, and so on. And we just printed for the one-to-one car, one of the largest pieces in the world, printed out of titanium, the exhaust piece. It saves almost 1 kilo to compare to our aluminium machined exhaust end piece. It's much more expensive, but very much lighter, and something very unique and cool to have on the car. As it's also far back, it's important to save a lot of weight there. We're also printing our variable turbine housing for our turbos for the one-to-one. It's very intricate shapes that we have found really difficult to cast. So we've had a great freedom of design when we 3D printed, as you're totally unrestricted of draft angles and things like that. So for production, we're actually 3D printing our turbine housings for our turbos to have the variable patented Koenigsegg solution. And we're going more and more into metal 3D printing, because at the low volume we're at, it is very costly to make production tooling and only making 10, 15, 20 pieces per year out of them. So we can actually use that as an argument to pay a lot for 3D printed metal parts, as we save tooling costs, we save tooling time, and we can make otherwise impossible shapes that are more efficient and lighter than our competitors can do, even if they're only at, well, a production volume of maybe 100 cars. They can't motivate the 3D printing cost, because then they save so much money by making a tool. But at this volume, we can motivate not saving the money by making a tool, because it doesn't cost much more at this production level to 3D print and get the benefit of otherwise impossible shapes. So pretty much all 3D printing works by the same principle. When you work with plastic materials like this ABS material, you have a table which is slowly moving downwards, and then you have a nozzle melting the plastic onto the table layer by layer. So in this case where you have kind of this hollowness, how do you print on the edge in the air? Well, it also prints a support material behind it, so it can stabilize and push onto that, and this will melt away in water after the piece is ready. So it's basically a table moving down and you're squirting out like cake material almost, and you're building support with another nozzle simultaneously where needed. The metal printing solutions are a little bit different. Basically they fill up the cabin with a thin layer of powder onto the table, of metal powder, and then they have a laser or an electron beam welding that powder together where they want, and then there's a scraper to scrape on another thin layer of metal powder, and then that's welded on top of the first area they welded, and then they spread up on another thin layer of powder, and then they keep on doing that until there is a metal part in a powder of the same material that you just shake off when you take it out. And that support material is usually made out of the same material as the part is made of, but it's only attached with very small fine points. You can fairly easily usually crack it off or knock it off and then fine polish the part. So in simple terms, that's how 3D printing works. It's pretty straightforward in a sense. There's also very exciting news coming out now of carbon fiber 3D printing machines, which we're looking closely at. So that could also revolutionize how carbon fiber is produced, and especially in low volume.